Let's start with a complete revision of GOC, purification techniques, and isomerism. Then we'll do problems based on that, previous year questions and anticipated questions. Let's try to finish it by 1 hour. Let's try. Okay, first of all, carbon has 4 valencies. Why is it so? Because the one atom will jump to the another p orbital to make it sp3 hybridized. Here we are first going to talk about the intermediates. Reactant to give the product, it have to go through the intermediate. Intermediates are the one which are short-lived species. Where it formed, there are two types of bond breaking, that is homolytic and heterolytic. Homolytic means same, heterolytic means different, right? So homolytic fission means it will form free radicals as an intermediate, like you can see, which is indicated by the fishhook arrow, right? One side arrow. And where it can happen, where the electronegativity difference is 0 or almost 0, like Cl2, F2, H2, so that each one of them will take up one electron. And you can see some reactions involve H nu or UV light. That time, mostly that will be followed by free radical mechanism. These free radicals are odd electron spaces. They are paramagnetic because that is having only one electron, that is unpaired electron. And these are chargeless spaces, doesn't have charges. And as you can see, this is how, this is sp2 hybridized and trigonal planar. But if I have fluorine in the system, which will pull the electron and also have lone pair of electrons in it, 3 lone pairs of electron in it. So that causes the repulsion in fluorine and carbon electron. So it takes up the structure of sp3 trigonal pyramidal structure, where the S character is less. And talking about the stability, tertiary free radical, carbon free radical is more stable because it has 3 alkyl groups, and then secondary, and then primary, and then methyl. These alkyl groups are considered as an electron donating groups. It is, as I told you, free radicals are electron deficient, so alkyls are also giving electrons, so which makes it stronger, right? Stable. Then the next one is heterolytic cleavage, where positive and negative part are created. So this can create a carbocation and carboanion. First, let's talk about carbocation, which will have 1 electron less. Cation is positively charged, right? C+. So these are electron deficient, electrons are less, and electron deficient compounds are considered as electrophiles. Electrophiles means electron loving species. And only 1 carbon is not there, which makes others are paired. So this is diamagnetic in nature, right? And there is an empty orbital. sp2 hybridized and trigonal planar structure, that is carbocation. Again, other alkyl groups which are electron donating, which is due to plus I effect. We'll see what is plus I effect in a while. So those are giving you electrons to the C+, which makes it tertiary as a stable one, then comes secondary, then comes primary and methyl. Then carboanions, these are negatively charged species because it is taking up the electron when heterolytic fission happens. So which will have a lone pair in it, unlike free radical. So 2 electrons with this. So this is electron rich, nucleophile and diamagnetic in nature. This is not an unpaired, this is a lone pair. And this is sp3 trigonal pyramidal. Okay, sp3 but not tetrahedral, trigonal pyramidal. And the stability also is just a ulta. Already this is electron rich. If electron donating group is giving more electron means, which makes it less stable, right? So that's why methyl, and then comes primary, then secondary, then tertiary, just opposite to carbocations. The next one is carbenes, where I have hydrogen or any atom that is taking up all those electrons like this, and then after that one more atom is also taking up, goes as in H plus and F minus here, which makes 2 electron because of one went as H plus, the another one goes as an F minus, right? Positive and negative part is relieved from the compound. Remaining I have 2 2 electrons and 1 empty orbital. Okay, so which makes 2 electrons. These 2 electrons can occupy 1 in the orbital like triplet, or 1 in the same orbital like singlet. Another one can leave it as an empty in case of singlet. So triplet carbenes are sp hybridized and linear, which are paramagnetic because it occupies 1 electron in each. It doesn't have any empty orbital. And these are electron deficient too, because this is unpaired. And the singlet ones, which will have sp2 hybridized and bent structure. It has 1 empty orbital also. This is electron deficient and makes it diamagnetic because both the electrons are occupying the same orbital. Comparing the stability of singlet and triplet, if hydrogen is present or very light molecules are present, then triplet would be more stable because singlet can produce a repulsion. If fluorine is present, it creates a back bonding because fluorine is having lone pair by itself and carbon that is having an empty orbital in case of singlet. So this gives electron to the empty orbital, kind of a coordinate bond, right? So which makes return gift, which makes the back bonding and makes the complex or compound much more stable than triplet system. It should have an empty orbital and lone pair containing compound must be attached. Then only back bonding can form. In that case, singlet is more stable than the triplet. Now let's move on to electronic effects, where we are going to see inductive effect, resonance, hyperconjugation, and electromeric effect. Let's see very quickly. Inductive effect, it's all about due to the electronegativity difference between the two atoms, it creates a slight positive and negative charges, create a dipole between these atoms, and due to that there is a pull of electrons. If more electronegative atom or electron withdrawing group is present over there, if electron donating group is present over there, that will donate the electrons, and this is a permanent effect, and this is distance dependent. Up to 3 carbons, this effect can be effective, and it operates only on the sigma bonds, not on pi bonds. It can be of 2 types, plus I and minus I. As I told you, if electron withdrawing group is present over there, that is pulling all those electrons towards it. For example, NR3, NH3, NO2, CN, aldehyde ketones, carboxylic acids, all those halogens, alcohols, ethers, everything. And in case of electron donating group presence, it is in plus I effect. It is donating the electrons like all those alkyl groups and carboxylate and oxides. Like you can see, it will get a positive charge and not a positive charge, it is just donating the electrons, and others can get a negative charge through it. And why that is so important? Because listen, here the acidic strength is dependent on the inductive effect. If minus I group is present, basically what is acidity? Tendency to give up the proton, right? Ability to give up the proton. So if there is an electron withdrawing group is present, then it will pull all those electrons. H plus can easily leave the compound, right? So acidic character will get increased. Similarly, if plus I group is present, it is giving the electron, donating the electron to it. So H plus can't easily leave the compound, which makes it less acidic character. Then stability, as we already saw in case of free radical and carbocation, tertiary becomes more stable because of this plus inductive effect. Resonance effect, the second effect, that is delocalization of adjacent p orbital electrons. Like we see, delocalization, it should have a conjugation, then only can undergo delocalization. And the conditions are, it should be sp or sp2 hybridized of all the atoms. There must be a double bond, conjugate double bond, or alternate double bonds, which means that parallel p orbital overlap to each other like this. The applications are stability. It will give more stability if there is more resonance structures are there. And how we can find which one is more stable? If there is a charge on it, then it becomes less stable. If electronegative atom gets a positive charge, that will also makes it less stable. And if there is more pi bonds, Then more delocalization resonance structures, so which makes it stable. And if there is a charge, that charge should be in the way. Electronegative atom should have a negative charge, and electropositive or comparatively less electronegative atom should get a positive charge. Let's say if I am having oxygen and carbon, carbon should have a negative charge, positive charge, and oxygen should have a negative charge. So then that makes the compound stable. Not stable as the non-charged species, but less than that. Okay, like this. Then the next one is mesomeric effect, where we have again plus M and minus M effect. Plus M effect are shown by electron donating groups, and minus M effect are shown by electron withdrawing groups. Like you can see here, this is the reason in case of electrophilic aromatic substitution, where electrophiles are directed towards para and ortho positions or meta positions. This resonance is important. Like you can see OH group, which is electron donating, which makes ortho and para positions are electron rich, so that the incoming electrophile goes to ortho and para positions. And similarly, in case of minus M effect, which makes ortho and para groups are positive in charge, comparatively meta is electron rich, comparatively. So electron rich will be considered as meta comparatively. So the incoming electrophile will go to meta position. Can you connect with this one with electrophilic aromatic substitution? That's why we are doing that. Then hyperconjugation. Hyperconjugation, which means there must be a sp3 hybridized carbon. So, which also called as a no bond resonance. One of those hydrogen will leave the compound and the charge are distributed, which will give you the more stability in the alkene. More the number of alpha hydrogens, which will give you more stability in case of alkenes. Like you can see here, 12 hydrogens are there in the first compound and 9 hydrogens are there in the second compound, which makes this as a more stable. Then the last effect, that is electromeric effect. That is a temporary effect. It's depend on what groups are approaching. Basically this effect, if electrophiles are approaching, it will take up the electron rich part and another carbon or another attached atom will become positive. If nucleophiles are coming into picture, then the another atom will become negatively charged, right? So that is what plus E and minus E effect, electromeric effect. It's depend on the attacking groups. Then comes aromaticity. Aromaticity, where we have 4n plus 2 Huckel's rule. The condition to be an aromatic is cyclic, planar. Each atom must be sp2 hybridized. It should have a conjugated pi bonds so that the delocalization can happen. It should obey 4n plus 2 pi electron rule. N refers to an integers starting from 0. So if you are substituting 0, 1, 2, 3 in N, you will get 2 pi electrons, 6 pi electrons, 10 pi electrons. That much number of pi electrons the compound should have. Like we say, take benzene. Here I have 6 pi electrons. And the next one, which is again 2 pi electrons. So not only the bonds, that is having a charges also, that should be in the way it can delocalize with the atom and makes it aromatic. Why the aromatic is so important is aromatic compounds are much more stable. Okay, what if that is not obeying this rule? We have two conditions. If obeying all the rules, like it's obeying cyclic, it is obeying the conjugated pi system and everything, but it is not obeying this particular 4n plus 2 rule. Instead, it is going with 4n rule. Okay, then that is considered as anti-aromatic, like you can see here. Anti-aromatics are unstable than the aromatic compounds. Then comes non-aromatic. Non-aromatic ones, which are non-planar compounds. Remember it like that. So they are non-planar compounds. Like you can see, this is tetraene. Tetraene, where I have 4 conjugated pi systems, but it is not planar. Why it is not planar? Due to the strain, angle strain happens. It takes up a double structure instead of being a planar structure. So only you have to know it is going to take up the double structure. then only you can answer this type of question. That's why I'm always saying you check out the worksheet attached below to get to know more about the compounds. So those are aromatic. If I want to range the stability order of aromatic, non-aromatic and anti-aromatic, aromatic becomes much stable, more stable, then the non, then anti. Let's solve these previous year questions from GOC. In Carrier's method for the estimation of halogens, 180 mg of an organic compound produced 143 mg of AgCl. The percentage of composition of chlorine in this compound is. Okay, so this is Carrier's method. So what we have to do is millimoles of AgCl, that is equal to weight produced divided by weight of AgCl, that is molar mass of Ag is 108 and Cl, that is 35.5, so which will become 143.5, that is 1 millimole. Okay, so let's find out the millimoles of Cl, which is in 1:1 ratio, right? So AgCl is 1 millimole, then Cl is also 1 millimole. So millimole of Cl, that is equal to 1. Let's calculate the mass of Cl now. So mass of Cl equal to 35.5, that is 1 Cl mass, molecular mass, gram per mole. So the mass of Cl, which is for 1 millimoles, so 10 to the power 3 grams, or you can write it as 35.5 milligrams. Okay, now calculate the percentage of Cl. Cl by mass, that is 35.5, and total mass, that is 180 milligram, which comes out to be into 100, that will be percentage 19.72 percentage. So nearest integer would be 20 percentage. Okay. Moving on to the next question. What is the possible number of stereoisomers for 5-phenyl pent-4-ene 2-ol? So pent 5-phenyl pent-4-ene 4-ene 2-ol 2OH, right? So they are asking possible number of stereoisomers. Here you can see this is in how many stereogenic centers are there. This side one group, another side CH3, OH and H. So this is one stereogenic center, and this is phenyl, and this part you can see this is one side and this is on the another side, which makes this as in one stereogenic center. So 2 to the power n, that is 4 stereoisomers are possible. One is for this Cis-Trans, and then this will have DNL. Here I have hydrogen attached with this carbon. Move to 1, 2, 3rd position, 2OH. Okay, 1, 3 position, that is triad tautomerism. Mostly the tautomerism or keto-enol tautomerism we will be seeing throughout 11th and 12th grade. Or isocyano tautomerism also we will see. Usually represents in the following functional groups like ketone, imine, nitro groups, which will exhibit tautomerism. At least one hydrogen atom on the sp3 hybridized alpha carbon atom must be there. Like you can see, alpha hydrogen must be there. Degree of unsaturation, sum of number of pi bonds and rings in a compound, we can find it using this formula. That is A plus 1 minus B plus C minus D divided by 2. So here ABCD represents CA, HB, XC, NDOE. So you can remember CHX. Yeah, no. Okay. Haloalkenes, no. So CHX, NO. If you're substituting number of atoms over there, like let's take C6H6, A plus 1, right? 6 plus 1 minus B plus 0 and 0 divided by 2, which will give you 4, which means I can have 4 unsaturation or a ring system in C6H6O. If you're writing a structure, like you can see, this is C6H5OH, right? Phenol. Where I'll have 1, 2, 3 as double bond and 1 as a ring. So total 4 degree of unsaturation. Likewise, you can check for C6H5I, C5H5N. Okay, where it is helpful to find the number of structural isomers. So if I want to find the structural isomer of C6H14, I'm getting DOU as 0, which means I don't have any double bonds or ring system. So only I can try it out with chains and branching. Okay, so that time it will be very much helpful. Then comes stereoisomers. Stereoisomers, the first stereoisomer is configurational isomer, where the spatial arrangement of the atoms are differing. It arises due to interconvertibility at room temperature. Like you can see, dog is there. I'm cutting this tail and placing or replacing, exchanging to one of this leg. Okay, so this is making and breaking of bonds happens. This is configurational isomer. Okay, then geometrical isomerism, where I have Cis-Trans isomer, which is super important. If same groups are on the same side, then that is cis. Same groups are on the opposite side, then that is trans. Like you can see C over H, C over H. When this case will arise? When there is a double bond or a ring system. In ring system, as you can see, C over H group, which is in the same side, and here that is in opposite side. Like you can see, which is in 3D structure, they have written it like same side, which is above the plane, and this is below the plane and this is above the plane. That makes it trans. Okay. In ketoxide also you can see this kind of type isomerism, but there we name it as E and Z isomer. Z means the priority groups. Priority groups, the lower priority groups are the, or a higher priority groups, which is on the same side. 1 on the same side, 2 on the same side. Let's take this carbon, where I have hydrogen and CH3. So CH3, that is having carbon as the first atom. So highest atomic number, then hydrogen. Higher atomic number, then hydrogen. So which makes it number 1 and hydrogen as 2. Similarly, if I have lone pair and oxygen, lone pair always gets least priority. Okay, so lone pair be 2 and OR is 1. So as you can see, here this is opposite to each other, which makes it trans, E isomer. And here I have same side, that is cis isomer, that we are writing here as Z isomer, Z. You can see the second example as well for ketones. Then conformational isomer. The first one we saw, that is configurational isomer. Here that is conformational. Because of the free rotation of CC bond. In configurational we saw double bonded compound and ring systems, which there is no free rotation. But here I have free rotation. Like you can see, if I am taking a dog, standing position and normally standing position, or jumping position and standing position, you can say. Those are conformational isomers, where the bond length and bond angle are same in all the conformers. In ethane, like you can see CH3, CH3, this is an eclipsed arrangement where the bond angles, the dihedral angle, that is having 0, 120 like that. Like you can see, eclipse, starting from eclipse 0 and then staggered, eclipsed, staggered, eclipsed, staggered and eclipsed. Okay. Keep the one carbon in fixed space. Let's say you are keeping the above carbon as a fixed space. Rotate the other ones. If you're writing H here, next write the H 60 degree apart. Next to 60 degree. Next to 60 degree and so on. Okay. Follow the H. You will get it. Okay. If I'm comparing staggered and eclipsed structure and which is more stable, eclipsed ones are having higher energy, so less stable compared with staggered. So in ethane, staggered are more stable. In case of propane, like you can see, staggered ones are considered. Here we have fully eclipsed, partially eclipsed, like that. So GAG conformers which will have both the CH3 bonds are together, CH3s are together, and which will have more spaces, like that. We have the conformers in that anti-conformation, which is more stable, which is far apart, 180 degree. That is staggered conformation. If there is a hydrogen bonding in the conformer, that isomer may be more stable than the other one, which gives extra stability. So usually gang, then comes anti, then partially eclipsed and fully eclipsed. Let's talk about optical isomerism, where we have chiral. Let's understand some terms. First one is chiral, an object that is non-superimposable on its mirror image, that is chiral. The property that is known as chirality. In achiral, just opposite, lacks chirality and the mirror images are superimposable to each other. Then asymmetric carbon means the carbon bonded with 4 different groups, and which is also known as stereogenic center or asymmetric center. What is optical activity? The substance which can rotate the plane polarized light, which means that is optically active. Let's say I am passing through the white plane polarized light to the compound. It either rotate the light to left side or right side. So depend on which rotation we decide what is the optical activity. So if that is rotating to the left side, then that is levorotatory. Then if that is rotating to the right side, then that is dextrorotatory. This is an experimental identification of the isomer D and L isomers. Okay, but all you have to know is if that is rotating to the right side or clockwise, then that is dextrorotatory D isomer. That is doing for the anti-clockwise, then that is L isomer. Here we have the term enantiomer. Enantiomer means if I have two isomers which are non-superimposable to the mirror image. Okay, and non-superimposable means, let's say I'm taking this part and placing it over here, which will not be matched, right? Which will not be superimposed. Likewise, D and L tartaric acid. Always optically active compound separations are done by resolution method. Diastereomer means they are non-superimposable, non-mirror images. Like you can see 3-bromo-2-butanol. These are diastereomers. I can't place it over, and also these are not mirror images also. Right? So if I want to write a mirror image of this one, then CH3, HBr, OH, H. So this is the mirror image, right? So if I am placing it over this compound, it is not fixing, right? Like you can see OH one side, H and Br, like that, right? So which is, these two are enantiomers. These are not mirror images, these are not non-superimposable, which is diastereomers, which can be separated. Diastereomers can be separated by physical methods like fractional distillation, crystallization, etc. This is the entire picture is given for enantiomers and diastereomers. Then here have a category meso compounds, which will have plane of symmetry that makes it optically inactive. For example, see this. This compound is optically active. Like you can see, the upper ones is very same as lower one. So this will have this is optically active. The upper part is optically active. Lower part is also optically active. But together if you see, that makes cancel out each other, which makes it optically inactive. Okay, that is what meso compound is. So the optical activity cancels due to internal compensation. Racemic mixture means the mixture of equal parts of D and L isomers which makes it optically inactive. For example, D and L isomer, both are optically active separately, but together that will get cancelled out. That makes it overall mixture, 50-50 mixture of mixtures, which makes it optically inactive due to external compensation. Quantitative analysis of organic compounds. Here I have listed all those formulas. For hydrogen, 2 by 18 into weight of H2O formed, weight of the substance into 100. Here, note on one point. In the top, in this place, whatever the compound you are getting, you have to mention the weight of that atom. Okay. For carbon, that is 12. For nitrogen, N2, that is 28. Okay. Sulfur, that is 32. Cl, that is 35.5, and so on. Okay, weight of the compound, weight of the atom as in the molecule, just mention it. And in the denominator, mention what is the compound formed from that atom. Here for hydrogen, H2O is formed. What is the weight of H2O? 80. Okay, molecular mass of H2O is 80. So that part you should not miss. Okay. Into weight of the H2O formed, weight. Okay, that how many grams? That weight. Divided by weight of the substance, overall substance into 100. Okay, for carbon again 12 by 44. Why 44? Because CO2 is formed. And nitrogen in 2 mass method 28 by 22,400 ml. So again volume of N2 at STP. STP, that's why 22.4 liters or 22,400 milliliters divided by weight of the compound into 100. In Gel-Dahl's method, we have a slight variation, that is 1.4 into normality of the acid. This is normality. Normality of the acid into volume of the acid divided by weight of the compound into 100. Okay, Gel-Dahl method modeling you have to focus while doing this because that is a bit different. Then Carrier's method of sulfur 32 by 233. Why 233? Because barium sulfate is formed. Chlorine 143.3 because AgCl is formed. Bromine 188 for AgBr. 235 for AgI. And for phosphorus 222 for magnesium pyrophosphate. Okay, simple. Which of the following conformations will be the most stable? As you can see, this is N-butane, right? CH3, CH2, CH2, CH3. So this 2 carbons are in the front and back carbons positioned over here, right? So for this conformation, I have already given you the gang that is more stable one where I have methyl on the opposite side. Let's see other options as well and then decide. So as you can see, option A is more stable compared to others because of strain and dihedral angle should be far away. And the next one, the isomeric butyrated bromide with the molecular formula C4H8DBr having 2 carbon atoms is having 2 chiral carbon C4H8DBr. So let's start trying this one by one. 2 bromo, this is butane, 2 bromo, 1 deutero. 2 bromo, 1 of those hydrogen, here is deutero, butane. This one, the second one is 2 bromo, 2 deutero, butane, and the third one is 2 bromo, 3 deutero. The fourth one, 2 bromo, 1 deutero, 2 methyl propane. 2 methyl propane. So as you can see, this is one chiral center, and this cannot be because I'm having 2 hydrogen and others cannot. And talking about this can become a chiral center, but CH2, CH3, this cannot. Talking about this one, this can be a chiral center, and this can also be the chiral center. Let's check D as also. This is having H and H, and this is one chiral center, this is CH3. So which makes option D as my right answer. Option C. Then the next question, identify the correct order of a given property. Identify the correct order of the given property for following compounds. Boiling point, density is given. Okay. So boiling point is depend on the 2-3 things, which is directly proportional to molecular weight and inversely proportional to branching. These rules remember, then others. Okay. Then let's see one by one. First one is having Cl 1, 2, 3 carbon, 2 carbons, 3 carbons, 1, 2, 3, 4 carbons. Okay. This is right. What about density? Density is also more or less same as boiling point. So here I have bromo, chloro and iodo. Density increases with atomic mass increases. So bromo shouldn't be here. It should be in the chloro position. So which makes it wrong. And then boiling point again. Branching. So branching is inversely proportional to boiling point. As the branching increases, boiling point decreases, but here, as you can see, I'm having bromo groups more, so which will increase the molecular weight, so which makes this as a right. And density, again I have iodo and bromo, bromo and chloro and bromo. So this is not right because chloro, bromo is there, and here I have only bromo, bromo and iodo. Its order shouldn't be like this. It should be density is directly proportional to atomic mass of halogen present over there. So clearly this is not a correct order. And what about E? I'm having same molecular formula, but the branching is the thing. So which makes inversely proportional to boiling point, right? So which makes it right. So A, C and E all are right. An organic compound A, C4H11N shows an optical activity and gives N2 gas on treatment with nitrous acid. A compound A reacts with PHSO2Cl, producing a compound which is soluble in KOH. The structure of A is. So the options given are amine, and then N with 2 methyl groups and 1 ethyl group, and this, And option D is primary amine. So they have mentioned C4H11N. It releases N2 gas on treatment with nitrous acid. So which must be N? Primary amine, because diazonium reaction, you remember. So which is treated with, let's say I have primary amine, it will produce N2Cl, which is unstable. So it will produce ROH with N2 gas. The compound A reacts with PHSO2Cl2, that is Hinsberg reagent, right? So producing a compound which is soluble in KOH. So after reacting with Hinsberg reagent, it forms a compound which is soluble in KOH. So hence the amine is primary amine. In the following halogenated organic compounds, the one with maximum number of chlorine atoms in its structure. Okay, so here you can see chloride, gamma, zine, chloropicrin and ferroin 12. You must know the structure of these, then only you can answer to this question. Let's quickly see this. Chloral, which is Cl3C CHO, chloral aldehyde group. And gamazine, that is cyclohexane with 1,1 Cl each. Then chloropicrin, we know picric acid, which is aromatic, but here I have nitro with 3 chlorines in it, and ferroin 12, that is CF2Cl2. So obviously gamazine becomes your answer. In the next question, given below are two statements, sulfonilic acid gives esterification test for carboxyl group, gives red color in Lesine's test for extra element detection. So in the light of these statements, we have to tell. So sulfonilic acid, basically this will look like yes, double bond O, OH, on the other side NH2, right? So it will not show any esterification test for carboxyl group, doesn't have any carboxylic group, and then gives red color with Lesine's test. Lesine test for extra element detection. So presence of both sulfur and nitrogen is there to give Lesine's test. So option statement 2, that is correct. Statement 1 is incorrect. Moving on to the next question. Total number of asymmetric carbon atom in testosterone. So let's see. Not this one. This one I'm having CH2 here. Here I have CH. This one. And this one. Also I have this one. OH groups in it, and then also this one. What about this? This is also a stereoasymmetric carbon. This one too, and this one. So total, how many? Not this one. Yeah. So total how many asymmetric carbon? 1, 2, 3, 4, 5, 6. The answer to this question is 6. Descending order of acidity for the following carboxylic acid is. So always remember, if you have electron withdrawing group, so that will increase the acidity and electron donating group will decrease the acidity. So let's see the compound CH3. Here I have 3 fluorines, great, Cl and Br. So fluorine is more electronegative, then Cl, then Br, and then least will be our CH3. So obviously B, so either option B or D, and then comes D or C. So it's C, then D, then A. Number of possible isomeric products formed when 3-chloro-1-butene reacts with HCl through carbocation formation. When 3-chloro-1-butene, 1-butene, 3-chloro with HCl through carbocation formation. So what we can see here is HCl will get added over there, just an addition reaction. So first H plus, so which will take up the electrons from the double bond, so which makes this as positive, and H will get added over here, so CH3. Then I have Cl. As a next step, either this lone pair can take up the proton, the positive charge will make look like this. Then Cl from the above side, it will attack so that it leaves to form ClCl. Or else what we can see is from here hydride shift is also possible. To form so this hydrogen can leave the compound as H minus, so hydride shift can happen to form this with the positive charge. This will take up the hydrogen, so remaining I will be having CH3 CH2 positive charge. Later the another chlorine will come and attack, which is on the same carbon. In this case, I won't be having any stereogenic center because here I have CH3, here I have 2 Cls, and this part I don't have any CH2, and then here I have CH3. But in this case, I can have 2 chiral carbon. Which can give 3 isomers above the plane, below the plane, or both are above the plane or both are below the plane, and this will be one product. So totally 4 products can be possible. They are asking a HCl to the carbocation, number of isomeric products possible, so 4 can be your answer.